All right, so we're moving on to chapter 11 today. Chapter 11 is all about radicals. The good news is there's only a handful of mechanisms that we need to know for this chapter. And it's the last chapter before our exam. So let's cover what a radical is. And I want to do this by comparing two different types of reactions. The first one involves heterolytic cleavage. And in heterolytic cleavage, you have two atoms that are covalently bonded together. And in this sort of reaction, you typically have a pair of electrons move on to one of those two atoms. And so you end up with X having a negative charge because it now has a lone pair, and Y has a positive charge because it's missing electrons, right? So in this sort of reaction, essentially you're forming anions. And the key is it involves a movement of a pair of electrons. This entire chapter, we're going to be looking at another type of reaction called homolytic cleavage. Where instead of moving two electrons, we're going to move one electron. So let's take this same pair. And in order to show movement of one electrons, we have to use different arrow notation. Specifically, we use a fishhook arrow, where there's only one half of that arrowhead. So one electron can hop over to Y, and one electron can hop over to X. When you do this now, X has one electron, and Y has the other electron. So these aren't quite anions. They're not cations or anions. Sorry, I should have wrote anions and cations up here. Instead of forming anions and cations, we're going to be forming radicals. Really, all a radical is an atom or a molecule that contains unpaired electrons. So we're not quite used to reactions where we're only moving one electron at a time. The big thing I've got to emphasize is you have to be super duper careful with your arrow notation. Like I was saying before, this arrow is not the same as the single-headed arrow. Anytime you have an arrow with that double arrowhead, that means it's a movement of two electrons. This single-headed arrow is always used for one electron arrow pushing. If you flip that up, you're showing a completely different mechanism. So be very, very careful with how you draw your arrows. So let's take a look at what radicals look like in terms of their geometry and their electronic configuration. So let's just take a super duper generic molecule where I've got some generic R groups bonded onto this carbon atom. And I've got an X group over here. This X group is going to fall off. And we want to show this cleavage homolytically. So let's go ahead and do some arrow pushing. So one of these electrons will hop over onto the leaving group. One will hop over onto the carbon. What do you think this resulting product will be in terms of its geometry? We've got all three of these R groups, and we've got this unpaired electron plus this leaving group that's got an unpaired electron. But what's the geometry of this guy?
Trigonal.
So let's talk about it with your neighbor and see if you guys can come up with an agreement.
Regional or
molecular.
molecular or regional?
What's that?
Which geometry, molecular or regional?
Either. Or both.
So it's going, obviously, if you get rid of the electrons, it's going to be trigonal.
If you get rid of the electron, it's going to be trigonal later.
If the electrons are regional, But for molecular geometry, it would be neutral because you include the electron. And it's not going to be so the
All right, give me a thumbs up if you and your neighbor are agreeing. A little bit. How many of you guys thought it would be trigonal pyramidal? A few people. How many of you thought it'd be trigonal planar? Some people. This one's actually a little tricky. All of the experimental evidence shows that it's actually trigonal planar, and I'll show you guys why. So this central carbon is out here, and we've got these R groups that are in plane with one another, so they're trigonal. And then we're left over with this p orbital, right? Because this carbon's now sp2 hybridized. That unpaired electron is actually super duper unstable, and it will be on both sides of that carbon essentially at the same time. That's that weird behavior of electrons you guys talk about in Gen Chem where they act like waves. Technically, they're occupying a statistical p lobe, right? So they can be on either face, and this is the most stable electronic configuration for radicals. So you end up forming a trigonal planar hybridization. And because of this, it's going to be sp2. So if you think about some sort of radical attacking in, this radical could attack from the top face or the bottom face of the p lobe. It really doesn't matter. The electron has equal probability of being on either side of that p lobe. The good thing with radicals is that they follow the same stability trend as carbocations, right? Carbocations are also sp2 hybridized. So let's make a note of that. So they follow the same stability trends as carbocations. So if you remember carbocationic stability, really we said resonance was the best feature, followed by tertiary, followed by secondary, followed by primary, which is way, way more stable than a methyl group. So this is our general trend. Luckily, we don't have to learn anything new. But then the question becomes, how do we draw resonance with radicals, right? We have to learn how to redo our resonance structures. Oop.
Does the radical technically do some sort of resonance between the top and bottom of the p lobes?
That's a good question. So the question was, when we look up here, I said that electron in that p orbital has equal probability of being on the top lobe and the bottom. That's not a true example of resonance. That's just a statistical probability. That's a good question, though. So let's take a look at how we draw arrow pushing for radical resonance structures. And I'll show you guys a molecule we're going to use a lot. This is an allyl group. And there's a bunch of hydrogens coming off of this, so let's draw them all in. One of these hydrogens I'll draw in as blue. These two I'll draw in as black. And then these two I'll draw in as green. This blue proton is referred to as vinylic. And then these green protons are referred to as allylic. And so let's try to pluck off one of those allylic protons. And so I'm just going to write minus H dot. We have to be careful not to do H plus because we're pulling off this radical. And let's take a look at the structure we would get out. So we still have this blue proton. We've got these green protons, and we've got this black proton. But now we've got one electron left over, right? Because if we're pulling off one of these allylic protons, one electron goes towards the hydrogen side and one electron goes towards that carbon, right? These allylic protons are a lot easier to remove than vinylic protons because the resulting structure is resonance stabilized. So let's try to do some arrow pushing to show how this is resonance stabilized. And we know we want to delocalize the radical to make it more stable. So if we delocalize it over here, we'd be forming half of a pi bond. What do you think we need to do?
To the other half.
Yeah, let's steal an electron from the other pi bond. Pull that over. We have one electron left over. That has to go somewhere. So we'll kick that electron over to the other side. I told you guys resonance wouldn't go away. Whoops. Let me clean this up. So we've got the radical now on the other carbon. And we've got our green protons over here, our blue proton here, and now our black protons on the other side. So these resonance structures are a little bit more complicated to draw. You have to remember to do the single fishhook arrows, and it usually involves more arrow pushing than your standard resonance structures, right? So be careful drawing these to make sure you're following the correct notation. Yep.
Is there a way to draw the resonance structure like you do the dotted line when it's a lone pair?
That's a good question. So you were wondering about drawing the hybrid structure with dashed lines. You typically don't do that with radicals because it can be very confusing. So I typically only do that with traditional resonance structures, not with radical resonance structures. Was there another question back there? No. Okay. So there are two main things that can stabilize radicals. One is resonance. We said that's the trump card. No pun intended. And then the second thing was hyperconjugation. So tertiary is more stabilizing than secondary, which is more stabilizing than primary. So let's do a little bit of practice. And I want you guys to help me draw some resonance structures for this compound where we've got pi bonds here, here, and an unpaired electron up here. So I'll give you guys a minute to work on this, but then check with your neighbor to see if you guys agree. And I'll give you a hint. There's two other resonance structures. So we'll make these worth 4 points each. And try to do all of your resonance structures with those single-headed arrows. So only move single electrons. Don't move entire pi bonds. Yeah, vinylic protons are protons coming directly off of your alkene. Allylic protons are one carbon removed.
Is there a name for the next carbon?
Typically not.
Vanillic.
Vanilla in the middle.
Allylic protons are named differently because they tend to be much more reactive than any other CH bonds. Once you think you got it, give me a thumbs up too. All right, looks like we've got a fair number of thumbs, so let's take a look. I'm going to move this electron down. We've got half of a pi bond. We need the other half, so I'm going to steal an electron from this pi bond. And then last but not least, I'm going to dump that other electron down into that lower corner. So now we've formed a new pi bond there. this pi bond was untouched, and our unpaired electron's now on that tertiary carbon. Looks good. So now I can go ahead and I can take this electron down. We need another electron from an adjacent pi bond, so I'll pull that one down. And then last but not least, this remaining electron will get dumped onto that terminal carbon. All right, so these are two additional valid resonance structures for that starting material. Be very, very careful when you're drawing these. It's easy to forget hydrogens or to violate arrow pushing rules. So try to just take a little bit of extra time while you're practicing these. Are there any questions on resonance?
So when we had the actual version, we would do like a partial double bond and partial charges. How do you do like a partial extra electron on those?
So typically with these structures, I don't draw any hybrid structures with the dashes. The reality is when you look at, let's say, this bond right here, it's in between a double bond in these two and a single bond in this structure. So it's not quite a true double bond. It's in between a double and a single like we saw during first term. But we don't like to draw hybrid structures with these just because it gets really confusing. And we'll come back to these allylic structures, I think, tomorrow. There's a unique type of radical reaction involving allylic radicals. But let's talk a little bit about some common types of radical reactions. And I'm going to introduce some terms. The first one involves radical cleavage. And with radical cleavage, it's exactly what we've been looking at. It's when you have two atoms that homolytically cleave, resulting in two separate radicals. So we've got X dot plus Y dot, each of which has that unpaired electron. The opposite reaction is also observed, where it's called radical coupling. And with radical coupling, you've got two radicals that essentially combine in order to form a covalent bond. And in order to show this, we essentially just have each of these fish hooked together in order to form a new bond pair. Easy enough, right? All right, so those are the two simple ones that involve relatively easy reactions. The next one involves an addition to a pi bond. And let's see if you guys can figure this one out. So we've got a radical, and we've got a pi bond. How do you guys think these could react? They could attack. So in this case, this radical wants to pair with something. It can't pair on its own. It needs another electron to pair with. It can steal an electron from the pi bond. So we could form a covalent bond there, but then we have an electron left over that will get dumped onto this adjacent carbon. So now we've formed a new covalent bond, and then this carbon over here has an unpaired electron. So we can add radicals into pi bonds, or we can eliminate. With radical elimination, it's essentially that top addition reaction in reverse. So now we've got this radical separating out into X dot plus a pi bond. And in this case, this radical will come down, grab an electron from that covalent bond, and then X will hop off as its own radical. And then last but not least, we have a class of radical reactions called abstractions. The first one is pretty easy. It's a hydrogen abstraction. And this involves a radical stealing a hydrogen. So this radical will reach out, pluck off this hydrogen, and then that R group will be given the remaining electron. And it's important to remember that in order for this reaction to be favorable, typically you're going to be forming some sort of stabilized radical, so usually a tertiary radical or resonance stabilized radical. It's similar to forming a carbocation in that way. And then last but not least, we've got halogen abstractions, which is very similar. And with halogen abstraction, you have some sort of radical that's stealing a halogen. And so I've got X drawn here, and let's make a little note. X2 is typically Cl2 or Br2. Chlorine is really, really, really reactive. It'll halogenate a lot of different things. Bromine's a little slower. Iodine is super duper sluggish, so it's almost never used. Does anybody know why fluorine's not listed on here?
Too destructive.
It's too destructive. So if you use F2, you've essentially made yourself a nice little bomb. I remember hearing about a chemist talking about fluorination chemistry, and he said, I'll give you 3 reasons not to do fluorination chemistry. And he held up his 3 remaining fingers. It is incredibly exothermic. Oftentimes it'll explode without any attributable cause, and typically people are avoiding it. However, there's been a resurgence in trying to figure out safe ways of performing radical fluorination. So in general, in our textbook, you will only see Cl2 and Br2, but if you look at more recent literature, there are some more gentle ways of doing radical fluorinations. So this will steal a halogen, and then a halogen will get kicked off as a radical. So these are the most common types of radical reactions. Yep.
So when we're drawing these and we're thinking about these, the radical's not actually attacking whatever it's pulling off. It's more like overlapping electron densities.
Yeah, exactly. The radical is getting so close that that covalent bond is weak enough to break and form a new covalent bond with the radical.
So it's not that it's attacking whatever it's taking.
Yeah, it's different than a nucleophilic attack.
And so we don't have to worry about charges or anything?
No, that's the unique thing with radicals is we're not forming anions or cations. These are both neutral, technically. They just have unpaired electrons.
Are they not even partial negatives?
Nope. Yeah, radicals can be true neutral compounds. They're just very unstable neutral compounds. We're very used to thinking of neutral compounds as being unusually stable, but radicals are kind of the outlier exception to that rule. All right, so let's take a look at some cool reactivity with these. And this involves just simple halogenation of alkanes. And I'll show you guys how I approach this sort of reaction. And the first thing I do is before starting, I identify which proton, if removed, would form the more stable radical. So identify the proton that, if removed, actually, I'm changing this, sorry. Hydrogen that, if abstracted, would result in the most stable anion, result in the most stable radical. We've got protons on the brain. Okay, so let's take a simple one. And I've got this alkane right here. So we've got methyl cyclohexane. And we need to determine which proton on methyl cyclohexane, I keep on saying proton, holy cow. Which hydrogen, if abstracted, which would result in the most stable radical. And so let's come up with some protons we can select. So we've got these red protons over here. Got a blue proton here. where I've got these 3 green protons coming off the methyl group. And I've also got these red protons over here, but they're essentially the same as removing the other red protons. Which one of these do you think will result in the most stable radical? The blue one, right? Because if we remove the blue one, so I'll do minus H dot, we would get a radical that is a tertiary radical. So let's keep our color coding going. And now we've got this unpaired electron coming off that tertiary position. So removal, whoop. The blue hydrogen results in a tertiary radical. That means that far and away that blue hydrogen is going to be the most reactive hydrogen on this molecule. So now let's approach this mechanism and let's see how this works now that we've identified the most reactive site. The first step of any radical reaction involves some sort of radical initiation. And with the radical initiation, it's pretty straightforward. You typically have some sort of halogen, like bromine or chlorine, and you're going to react it to some sort of high energy condition in order to homolytically cleave it. So the conditions that are used are either high heat or UV. And chemists like to indicate UV light with Planck's constant times frequency instead of writing UV. Don't ask me why. We just like to be difficult with physicists. And so when we do this, we're going to get homolytic cleavage. These bromines will pop off each side, and we'll end up initiating our reaction by forming some radicals, specifically 2 bromine radicals. Step 2 is referred to as propagation. Propagation just results in one radical reacting with another and then forming a new radical out of that. So when we do this, we've already identified our most reactive proton, or hydrogen, holy cow, Br dot. And it's going to abstract this hydrogen. The remaining proton will be put on that tertiary carbon. However, you'll notice at the end of this reaction, we formed a new radical and we formed a covalent bond. So we've made HBr and an organic radical. That's why this is referred to as propagation. Is now this radical can react with another equivalent of bromine and pluck off a halogen. Actually, let me clean this up. It's going to steal one of these bromines, and then the other one will get ejected off as its own radical. The key portion of this propagation step is you're regenerating your radical. And essentially, it can go on to react with more equivalents of your starting material in an infinite loop, right? So this can go on over and 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 over again until it essentially runs out of that methyl cyclohexane, right?
Couldn't it also run out of bromine? Then you wouldn't be able to.
Yeah, you'll either run out of your bromine or you'll run out of your methyl cyclohexane. And then the last step is eventually, when the reactions run out of that starting material, it will exhaust itself and it will have to terminate. And there are three options with termination. The first one is pretty straightforward. It involves a coupling of two halogens. So let's say we've got two bromine radicals that ran out of methyl cyclohexane to react with. All they'll do is couple together and reform bromine. The other option is, let's say you've got a trace amount of your methyl cyclohexane and you've got a trace amount of your bromine radical. These can react and you can get one more molecule of your product. Or, last but not least, you could have two equivalents of your methyl cyclohexane radical that couple together and form a new carbon-carbon covalent bond. However, do you think that's going to be very likely? No, it's pretty sterically blocked, but it's somewhat possible, albeit unlikely. So we'll draw it in there just to show it as an option. So in terms of termination step, I'll allow you to pick any of these three to show at least some termination step where you eliminate your radicals, meaning you go from having a radical to having no radicals out. All right. One important thing to note, though, is if you add in an excess amount of reagent, it'll keep on going and find more sites where it can react. So let's take an example of this. So let's make a note. If excess halogen is present, it will continue and react at the next best site. So let's take an example of this. It's actually a commercial example. For this example, let's say we've got methane. Methane's natural gas, right? We can get this out of the ground. But let's say we want to turn it into a solvent for an organic chemistry lab, right? In order to do this, what they do is they take chlorine gas and they have this in excess amounts, and they slam this together with methane under UV conditions, and we end up making CCl4, that carbon tetrachloride. That was one of the solvents we used with our halogenation of alkynes. So we made a halogenated organic solvent. You also get a small amount of chloroform out. That's the equivalent with 3 chlorines. You also get a little bit of dichloromethane out, which we've used in lab before. That's a good organic solvent. And you end up with a little bit of chloromethane. Each of these has distinct boiling points. You can distill them off and isolate them as pure organic solvents. So if you're not careful, especially with chlorine, it will overreact and add chlorine into all sorts of wacky positions. So you have to be very, very careful with how much you're using. Does that make sense?
What do you get for the most of this? Or does it really depend on the conditions?
It depends on the conditions. Typically, in industry, they refine this and they'll try to narrow it down to minimize the side products that they don't want. So let's,
Can I ask a question?
Yeah.
For the 3 options for termination, you said the third one's not as likely. Are the other 2 as likely as each other?
yeah, it's really that they occur in trace amounts. It depends on the reaction conditions, though, too.
Okay.
Yeah. I'm fine with you showing any termination step, so long as you show the radicals going away. All right, let's talk about regiochemistry a little bit. What does it mean when I'm talking about regiochemistry? Yeah, which constitutional isomer are you forming? So let's take a look at this example. So we've got 2-methylpentane, and we're going to react this with chlorine under UV conditions, and then we're going to react this with bromine under UV conditions. We know that the proton coming off that central carbon is going to be the most reactive. So with chlorination, the main product we'll see is chlorine coming off there. However, we also observe a little bit where chlorine actually comes off that other side. Same thing's true with bromination. You can imagine the analogous example. And we could carry out this experiment and determine the ratio of each product. For the chlorination, we get approximately 72% of the product we would anticipate, and about 28% of that side product, right? With bromination, it's approximately 100% our desired product, and approximately 0% of that undesired product. So the moral of this story, bromination is a lot easier to do. Chlorination is known as a promiscuous reaction, meaning the chlorine will end up attacking any carbon that's really available, and you get this statistical mixture of products out of it. Where bromination is really selective. It's only going to attack that most stable position. That also brings me back to the fluorination example. You remember how I said fluorination is explosive? Another problem with fluorination is it's even less selective than chlorination. It'll react at any carbon that's available that has a proton or a hydrogen on it. So that's another reason why it's really not used as often. Does that make sense?
So is it chlorine's able to force the bond because it's so reactive with any of them, but it's still more favorable to the more stable one?
Yeah, that's a good question. So let's think about this from an energy landscape, right? So you guys remember our reaction coordinate diagrams? So if we think about this from an energy landscape, bromine's a nice big atom, which means that radical or the unpaired electron has this big electron cloud to hang out in. Chlorine, on the other hand, is much smaller. Whoop. Sorry, let me change this a little bit. We'll do Br dot. Chlorine's much smaller, which means this radical, this radical is going to be much, much higher in energy. That electron's not happy being in a small cloud. So if we think about this activation energy, right, going to each of these products, we could say this EA for bromine requires a bigger uphill climb than the reaction with chlorine. That means because the EA is so much lower for the chlorine radical, it really doesn't care what it's reacting with. It just wants to get over that hill and form something more stable. So really it has to do with the instability of the chlorine radical. Yep.
So from a kinetic standpoint, since bromine's a larger atom, doesn't that mean that the electron essentially has more kinetic energy by virtue of how much distance it's traveling around?
Yeah, it's not really kinetic energy so much as just the electron cloud that unpaired electron has to roam in. In bromine, it's got this giant electron cloud.
But that's what I'm saying. Would it be going faster around because it's farther out and it's farther from the center when it's spinning?
No, it's not really a matter of how fast it's going. It's just the amount of the area it has to be in.
Okay.
Yeah. So you can imagine fluorination would probably be up here. And it would have almost no hill to run over, which means you're essentially playing around with something that's going to react whether you want it to or not. It's super duper unstable. All right, so let's change gears. We talked about stereochemistry. Let's finish off talking about, or we've just finished talking about regiochemistry. Let's talk about stereochemistry. Let's take this example. Here we go. And we've got bromine, and we've got UV light. Let's try to determine what our product would be for this radical bromination. Four points. So let's go ahead just for fun and do the mechanism. So we know step one is initiation. That's where we form our radical. So in this case, we've got Br that's going to be cleaved by this UV light. One electron goes to this bromine, the other goes to that bromine. And we've got two radicals. What was the next step? Yeah, propagation. And with propagation, we have to find the hydrogen that's going to be most reactive on our starting material. Where do you think that hydrogen is going to be? Yeah, coming off the tertiary position. So let's do propagation. And with propagation, oh my goodness, we said it's going to be that tertiary carbon. And we've got this proton hanging off here, and this bromine radical is going to come pluck off that proton. Let me change the color here. I'll fix it later. And then the remaining electron is going to get dumped down onto that central carbon. And we've made an equivalent of HBr. And then in the next step, we said we need to regenerate our radical. So it's going to grab another halogen off of Br2 and kick off a bromide. However, do you think we're going to get one or two products out of this?
Two.
Why do you say that?
Because we're doing stereochemistry.
Because we're doing stereochemistry? That's a fair bet. Well, let's think about this, right? We said our radical is going to be trigonal planar. Which means that that radical can form a covalent bond from the top lobe or the bottom lobe, right? So that bromine could be delivered to the top face or bottom face. So let's draw both potential products out. So for the first one, we'll draw it coming in from the underneath side. For the other one, we'll draw it coming in from the top side. What's the relationship between these? Yeah, we formed a mixture of enantiomers. So we'll just say racemic mix of enantiomers. And then last but not least, we've regenerated our radical, and that could continue on and make more and more of our product. And then in our last step, what was it again? Termination. And in termination, you can pick any two radicals that are around in solution and have them coupled together. You don't have to show them all. So for this example, I'll just show these two bromines forming a new covalent bond. So really, it's important to remember that if you can form a stereoisomer, or if you are forming, or sorry, let me rephrase that. If you're forming a new stereocenter, you need to consider the fact that you might be forming some stereoisomers out of it. All right, tomorrow when we come in, we'll do some more practice, and then we'll talk a bit about allylic halogenation.